In this talk, we will introduce our recent CVPR work. DINER, Disorder-invariant implicit neural representation. The contents include 5 parts. The first question is, what is implicit neural representation? Let's revisit the traditional explicit representation. Traditional representation saves the information of a signal as a matrix. On the contrary, the DINER saves the mapping function between the coordinates and the attributes. Most DINERs use the multilayer perceptron network as function approximators. Compared with traditional explicit representation, DINER has 2 advantages. Smaller storage cost. Plug-to-play advantage for optimizing inverse problems. DINER has plug-to-play advantage for optimizing inverse problems. By representing the signal to be optimized using DINER and encoding differentiable physical mechanisms into the loss function design, such as the Raymarching rendering, Fresnel diffraction propagation and partial differential equations. DINER could be applied to solve different problems, such as the PDE optimization, novel view synthesis and 3D cardiac. As a result, it is necessary to design an DINER with lower complexity and higher capacity for faster and more accurate inverse optimization. The performance of DINER is limited in 2 aspects, the network structure and the distribution of signal self. From the first aspect, current DINER are suffered from a spectral bias. It tends to learn low-frequency information and is not good at representing high-frequency contents. In the left top figure, the fitted results are oversmoothed. Existing solutions often focus on adding more neural network layers, encoding high-frequency contents in the input or activation functions. However, their solutions result in more training time. Additionally, the expressive power of DINER is still restricted to functions that can be represented using a linear combination of certain harmonics of the pre-encoded frequency. Another factor is the distribution signal self. Given an DINER with fixed network structure, discrete signals arranged with different orders will be represented with different accuracy. Such as the baboon and the Lena here, when they are arranged with different orders, different fitting accuracy are obtained. It is noticed that the sorted images have the highest PSNR values since the most low-frequency contents are included. To solve these problems, we propose the DINER, the disorder-invariant DINER. DINER is very simple. Compared with traditional DINER, an additional full-resolution hash table is introduced between the input coordinate and the subsequent network. Given an input coordinate, the corresponding hash key is indexed from the hash table for feeding into the subsequent network. During the training process, both the parameters in the hash table and the network will be. It could be easily proved that the DINER is disorder-invariant, that signals with the same histogram distribution of attributes share an optimized network with the same parameter values. If you are interested, please read the paper for details. The right figure shows the fitted results of the baboon arranged with different orders using the DINER. It is noticed that they share same PSNR values. The left panel visualizes the hash table. The left column shows the original signals, the middle column shows the rearranged signal, or in other words, the learned hash table. It is noticed that the rearranged signal appears to be composed of low-frequency contents. As a result, even a tiny network in DINER could achieve very high PSNR. To vary the performance of the DINER, we applied DINER to represent 2D image and 3D video. We combined DINER with different DINER backbones, MLP and Siren, and compared with current state of the arts. DINER has more than 15 dB advantages on image fitting. For representing a 3D video, DINER uses less network parameters and achieves a much higher PSNR value, more than 14 dB advantage. We applied DINER to 2 inverse problems. The first problem is phase recovery in lensless imaging. The imaging model of the lensless imaging could be formulated as the function. The goal is to recover the amplitude and phase of the sample from known measurements. Point spread functions and illumination. We model the amplitude and phase of the sample using the DINER, where the input is the coordinates, x, y, of the sample, and the output is the corresponding amplitude and the phase. We compare our results with 3 SOTA methods. Recent proposed FisnNet and our previous method DNF. Additionally, the recent proposed SOTA DINER backbone instant NGP is also implemented using the lensless imaging model. Our method could provide reconstruction with higher PSNR values and much faster convergence, over 100x advantages. We also applied DINER to the 3D refractive index recovery in intensity diffraction tomography. The imaging model of IDT is formulated as the function. The goal is to recover the unknown refractive index of the sample from the known measurements. Sample intensity mapping and refractive index of background. We model the complex-valued permittivity of the sample using the DINER, where the input is the coordinates, x, y, z, of the sample, and the output is the corresponding complex-valued permittivity. After that, refractive index is recovered using the second equation. We compare our results with the SOTA method DCOF. Our method could reconstruct more details with less training times. Because the hash table maps the signal into another one, the neighboring coordinates are far away from each other after the hash mapping. As a result, the DINER could not process continuous signals. Thank you for your attention.